discussion on advertising systems, search advertising systems that we just started talking about last class. And as I said, if I didn't say, then I will say that every class could be converted into a whole course. Classification can be a course, classification can be a course, or both of them together can be a course, and advertising can be a course. And in fact, this link here, it's actually, it's going right now, there's a course that's going on at Stanford by two guys in Yahoo who actually know a lot about search advertising, and they're running an entire course just around that. Okay, so we'll just do it in one class. They're much faster than that. But if you want to go slower, then you can read more information there. Okay, and then after that, I am going to start talking about the third part. I don't know which part is third part anymore, but the last part of the course is exploiting and specifying and exploiting structure. Remember, in the very beginning of the course, we said if you have structure, then you can ask more interesting queries. And until now, we basically never really looked that much at structure. In fact, the only time we looked at structure was when we had HTML tags. And we sort of said anything in the header will get slightly more importance than anything in the footnote form. So if you give some structure, I can use it, essentially. So we will look, the rest of the course actually after this topic is about how to specify and extract structure. Either you specify structure, or if you don't have a way of specifying it, extract it from the non-unstructured data. And then how to use it, okay, which is basically the last part. Okay, before I go on advertising, are there questions? Yes?
I was looking at the rest of your schedule. Did you actually have a second midterm exam, or was it just the final?
Did I write second midterm exam?
Is there?
I didn't know that I wrote.
I don't think, no, you didn't. I just wanted to
No, there
say.
is no second midterm, no.
And the final's comprehensive?
Yeah. Well, I mean, yeah, I think so. I mean, unless I tell you otherwise.
Okay.
Other questions? Yeah.
Content-based filtering. You said content-based filtering is domain sensitive. Domain sensitive. How can you give an example or something? Because from what I understand, it's all based on text. So are you trying to say that if you have content-based filtering for, say, the movie domain, you cannot?
No. So that's an interesting question. So for example, first of all, in general, content-based filtering depends on there being features. Okay, if you just happen to assume that words are features, then presumably, yes, in fact, it becomes, the domain there is just word feature. Okay, and then there are many, many normal domains that can be written in text. Okay, a more useful way of thinking about it, that's a good question actually. So mostly people are talking about the fact that for the restaurant, the attributes were whether he will wait, I mean how many patrons are there, etc. And if it is something like the movies, then it might be, is it an action movie, is it something else? Is it an action movie, is it a sad movie or a happy movie? Does it have, is it an ensemble movie or is it a single character movie? These are all the features there. Okay, now if you ignore all the features and just go with the text description of the movies, then yes, I mean, then basically it becomes domain free there, in the sense it just becomes only in terms of words, except those are going to be useless. I mean, your predictive power would be much, much less if I just go with words. Okay, even for book descriptions, you notice that you essentially talk about title and maybe reviews and maybe price, etc. And each of which are bags of words. So instead of just thinking of this as undifferentiated mass of words, you tend to think of them as vectors, vector of bags. Okay. Whenever you're doing this, then you are sort of talking about what are the features that are relevant to the domain under consideration.
So you're basically doing it so that your prediction levels can go up.
Exactly. That's very much the case. So if you start from text descriptions and you try to make sense of this, yes, you can do that, but your prediction level will be lower, basically.
Because it seemed to make more sense. For example, if somebody buys a couple of sports products, say a football or something, and he also reads book, I have the data that this guy reads books also. then it makes sense to recommend him sports.
But that is not going to be written anywhere in the text description of those books, for example. In fact, that is a classic example where the text description of books may not have anything about text description of sports. And yet, one guy just put them together because essentially you are now defining them in a different feature space. You're defining in terms of the users who use them together. Okay? Other questions? Okay, so last class we were looking at the advertisement, search advertising and the history of search advertising, and also talked about, we looked at the history of search advertising, and then the fact that there are, in understanding search advertising as a recommendation system, it's somewhat different from normal recommendation systems because it's a three-party situation, not a two-party situation. In normal recommendation systems, it's either one party or two party. Okay, in the search advertisement, there's basically three parties. The search engines who want to show you advertisements so that if you click on them, they get money from the advertisers. Okay, and the advertisers who assume that if you somehow get into their shop, then you might buy something. And then you who actually just probably don't want to see any advertisements at all, but if you are forced to see advertisements, you would like to see the ones that are sort of relevant to you. Now the same word, relevance, as again, just as we talked about, we want to see relevant results for the queries. Similarly, we want to see relevant advertisements for whatever we are doing at that point. Okay, so those are three different parties and their utility measures. So in some sense, if you're talking about what's the best search advertising system, somehow it has to take into account the utility metrics of all of these, all three of them. Okay, so from the point, but the interesting question of course is, sometimes they are synergistic, they kind of mesh well, sometimes they're actually, locked horns, they don't actually mesh well. Okay, so that was what I was talking about at the very end of the class. So advertisers, let's see. So basically these are the three parties, and there can be conflicts and synergies in the sense when you, for example, search engines as well as advertisers want more clicks. So they both like to get more clicks. Okay. Search engines and users want good ads because if there are no good ads, then people are not going to click. So search engine is unhappy. And if you are forced to see bad ads, then you get, probably dissatisfied with the search. The fact that there are already advertisements, but there are also crummy advertisements might make you feel much, much worse off. So that's the user thing. And the only thing users can do is withhold their click. If they get, if they get annoyed, then they won't click, basically. Okay, and in these cases, at least search engine and advertisers, search engine and users have synergies, but not all three together. Okay, and similarly here, conflicting utilities, higher cost per click is better for search engine, but it's worse for the advertiser, right? And similarly, if I show lots and lots of irrelevant advertisements, these get to annoy the users, but maybe some of them will get clicked, and so advertisers and search engines will still do fine out there. Okay, in fact, I don't know how many of you, I think I probably clicked on advertisements on the site maybe once, and after that I put ad block, so I haven't clicked. So again, as I said, don't look at the world based on your lifestyle, then you will design crummy products, okay? Right? Because there may be people who apparently, click on these advertisements. That's why Google is as, rich a company as it is. So coming back to this, if you're talking about how to do this, the search advertisement system, then you need to kind of balance these utilities. Okay, so at some top level abstract way, I would say the utility of the overall system is somehow a combination of the utility of the advertiser, the user, and the search engine. Some arbitrary function. And then you have to figure out what that function is, and then you need to write it as an optimization problem. Okay. But that's normally pretty darn hard. So instead, you might essentially, for example, a simple idea might be that somehow it's some linear combination of the utilities. Even there, you need to sort of figure out how to give utilities for each of these. Maybe the search engine and the advertiser, their dollar value is their utility itself. I'm sorry, for the search engines, the dollar value is the utility. For the advertisers, it's already intangible. The number of converted sales is the utility. eventually. Just people coming onto your store and going away is making you poor, making the search engine rich. And that's not useful, right? And then for users, it's the relevance of the ads. Did they get any sort of fun clicking this and some satisfaction clicking this? So somehow you need to combine these, and maybe you can think of linear, but that's just generally too hard. Mostly what we will be looking at and what people try to do is, because it's a complex enough optimization problem, you try to maximize, and then furthermore, it's a complex enough optimization problem, and B, all the chips are controlled by the search engines. In essence, they are taking the bits, they are showing the results, right? So to some extent, if they really screw up, then users will leave the search engine and the advertisers will leave the search engine. But there is a reasonable amount of margin where they can play the game, right? And so we could think of basically, instead of this huge optimization problem as if it's done by a fourth party who is neutral to all these three parties, you realize that it's actually done by sort of a search engine. So the search engine would be trying to maximize per search revenue, okay, subject to some reasonable constraints, saying don't make user utility fall too below. Maybe at least it should be greater than alpha. And then advertisers' return on investment, let it not fall too much below. You see what I'm saying? So you went from an optimization problem into a decision problem. Well, it's a multi-dimensional optimization problem into a single-dimensional optimization problem with two decision constraints. That's what you do. Okay, even this is mostly here to kind of make you think of the complexity of the overall problem. Okay, so what I'm going to do next really is start from the simplest case and start adding complexities, start adding twists. Okay, by the end of which there will be enough twists and you might very well know how to handle each one of the complications independently. That's the hope, that at least you will know how to handle each of the complications independently. But as I'm talking about it, in the back of your head, you have to keep thinking, well, you handle this problem, this problem, this problem, but all of them have to be handled together. Would it be the case that the solutions will, for individual problems can be just added together? Okay, that's something that, really I will end the lecture by saying all of them have to be handled together. But I will tell you at least how to handle pieces. That's more or less what you can expect. Okay, so the simplest case of the advertisement problem is the following. Okay, so I would just think of there being a stream of queries coming to the search engine. Okay, and the advertisers, they have bid on the queries. They said, if somebody asks query Q1, then we want our advertisement to be shown to that user. And if they are asking for query Q2, we want our advertisement to be shown to the user. Okay, and so they basically, since all of them want to be shown, then the search engine basically says, okay, if I were to show them your advertisement, what do I get? And in the old print media, just showing itself, the search engine should get you some money. So if I print an advertisement, so imagine New York Times is making specialized editions for each home, then just to show somebody's advertisement in your edition, then they will take some money upfront. Okay, but search engines basically say, well, you don't have to pay us right away. If the guy clicks on your advertisement, then you have to pay us. And you would pay what we have, there's a contract agreement we get into upfront. Okay, so for example, each of these guys say that, okay, I will pay for this query, for query Q1, A might be saying I'll pay $5. Nobody actually pays $5, but let's say 5 cents if they click on this, my advertisement. Okay, and B says I will click and pay 8 cents if they click on my advertisement. Somebody says $10 if they click on my advertisement. Okay, now the queries are coming one after other after other. Okay, and remember that you have to make a decision for each query as to which advertiser to show. And one more simplification I'll make is for each query you'll only show one advertisement. So you notice already I made a lot of simplifications. You know how advertisement already sort of works. That you see that I've already simplified the problem down to queries are what people are bidding on, and you are only essentially showing one advertisement per query. And these queries are coming in a stream, and for each, then you have to pick an advertiser. Okay, and let's assume in this particular case, all I really care is to maximize the revenue that the search engine gets. Okay, now notice that if I were to tell you by now until evening, the following, I'm sorry, this is already evening, by now until midnight, the following 10 billion, the sequence of 10 billion queries will come. If I were to tell you that, okay, then you can actually look at all the bids that people have and then make a single decision saying, what are all the advertisements you're going to show from now until midnight? That would be solving this problem offline and then executing it. But you can't actually use that because you don't know what queries are going to come from now until midnight. So in some sense, you need to make decisions as the queries are coming in. Do you understand what I'm saying? So this is a scenario where had somebody given you all the queries up front, even though this problem might be easy enough, but if, here is a kind of problem where if I have told you what are all the queries that are going to come, right, then you may be able to decide who should you show to each of the queries once and for all. But right now in this case, you don't have that information because the queries are coming one by one. Okay, so you need to make an online decision. Okay, which for this particular case is easy enough, but online decision sometimes can get you into trouble. Okay, so if you're solving a problem using online decision, so for example, I gave you a long 20-page midterm, and I keep telling you guys, please look at all 20 pages once, just 10 seconds spend looking at all the 20 pages before you start spending time on answering queries. Why? Because then you will know where are the easy problems, where are the hard problems, and you can make a globally optimal decision as to how to do the midterm. What do you guys do? You want to do online decision making. Okay, the first problem is LSI. Let me spend my waking hours doing LSI and then say I have no more time left. Okay, so here is a situation where the problem could have been done both in online and offline fashion, and you chose to do it in online and you pay the price. Okay, in general, if a problem can be done both in online and offline fashion, the optimal solution for doing it offline cannot be worse than the optimal solution for doing it online. Do you understand what I'm saying? You would never ever ask people, unless you have this kind of a problem, that the very fact that there is an LSI problem in the 14th page, kind of terrorizes you so much that you can't do any problem starting from the first one. What's your name? I forgot because there's an LSI problem, right? In that case, it's not going to help, but in general, for normal people, having extra information is not going to worsen their performance. Okay? So we are basically looking at online algorithms here. Okay? In this particular case, it turns out that if I were to, the simplest online decision I can make is as soon as I get a query, I look at the user who has the advertiser who has the best bid for that query and pick that advertiser and show that. This is an online version. It turns out that that greedy algorithm in this case is optimal because there are no other constraints. In some sense I'm saying advertisers have infinite amounts of budgets. They're willing to pay forever and ever. Okay, and you're only showing one advertisement per query. And so in essence, the online version, which is to maximize search engine revenue, basically you need an online algorithm and a greedy algorithm, which is just picking greedily the advertiser who is paying the most for this query, okay, is in fact also optimal. Okay, when you're talking about online algorithms, there is this whole technical point called competitive ratio. So what's competitive ratio? So have you seen the midterm end to end once and decided the optimal way to do the midterm, and then based on that you are going to get 56 marks on the midterm, and you did just online that let midterm just come in the order it is coming and I'll try my best, okay, and then you got 47 on the midterm, then your competitive ratio of your decision is basically 47 by 56. In some sense, remember, even when the questions are coming page by page by page, you get to decide when to give up. I think most of you realize that spending, 1 hour 40 minutes or 1 hour 10 minutes on the first question is a little too much when there are 19 more pages left. Okay, so you will do some kind of a decision online saying, okay, I'm not going to spend any more time on this paper, on this question. I'll go into the other questions. So then you will not still get the optimal amount of marks. If you are smart, all of you think you are that smart in making these online decisions. That's why you don't want to waste those precious 10 seconds looking at the rest of the exam, right? And so if you're really smart, then the competitive ratio for you should be 1. Do you understand? So it's not that looking at the entire exam would have given you 65. If your understanding of the subject is about 10%, then you would never get 65 out of 65, right? But you should get whatever you're supposed to get, at least, and that's basically the competitive ratio. So the best an online algorithm can do is to do as well as an offline version which has all the data in front of it, and then used it to compute the optimal way to solve the problem. And then, if you compare the performance of the online versus offline, that's called the competitive ratio, and that's always less than or equal to 1. If it is 1, you are a really lucky person. You got a really smart online algorithm. Okay, so it turns out that for this simple scenario, just greedy selection is an online algorithm, and it has competitive ratio 1. In this case, you can't do any worse. Even if you had all the ads in front of you, you wouldn't have done anything different. Because there are no additional constraints. Okay? The way things will become interesting, we'll see in a minute later on, if people have budget restrictions, then suddenly you want to know, to show what. Okay, but we'll get to that later. Okay, so this is the simplest case. Now I'm going to start. Did people understand this? This is the simplest kind of search advertising. Okay? Yes?
How do the advertisers wait for query?
Let's assume that they said basically that I'm going to pay $5 for Q1, $3 for Q2, $7 for Q3, and so on. That's what they said. No, there is a way they actually bid. They specify their bids upfront. In fact, by the way, okay, I seriously suggest that all of you, if you have Gmail account, like Google account, you all have free advertising budget. As far as I know, they keep bothering me saying, we put $10 in your analytics budget. Why don't you make a query? And why don't you sell stuff? eBay used to ask me to sell my entire home, and now they are asking me not to sell entire home. Right? I would suggest that you make a query and play with it. This is a great way for understanding what they're asking. So basically, you can make your own advertisement. I would suggest, for example, just as an idea, all of you should advertise cse494. Right? For any possible interesting query, cse494 advertisement should come first. Okay, you can pull your advertisement and make it the advertisement that comes anytime anybody is looking about ASU. Forget about football and Kerry Business School, which is what we keep seeing. Okay, so that's the way you actually can figure out. You set the bids that you are putting. Okay, and in fact, that's a full thing, and all of you can do it. All these search engines, certainly Google and also Facebook, they all make this interface easy enough that anybody can put advertisements up. In fact, this is the whole point, right? This is, in the old days, people who will put advertisements are those who have deep pockets. And they will put like full page advertisements or half page advertisements and so on. Now anybody can put advertisements for anything. As I said last class, the guys who are running that course, they put an advertisement saying, come to this course. And you can play with this. Okay? Anyway, so any other questions on this? This is the simplest case. Okay, if you lost here, then you lost anyway. Okay, so the first complication I'm going to look at is, suppose one guy says, for this query Q1, I'm going to pay $10, and the other guy says I'm only going to pay $5. My previous example, I'm just saying my idea is to pick the $10 one. But what if, remember that it's not enough, as soon as I show the advertisement, I don't get the $10. I have this, pesky user in the stream, and the pesky user has to click on it, right? If the user doesn't click, then there's no point in showing the advertisement because you won't get any money. Now suppose the guy who's paying $10 basically is writing probably borderline offensive stuff in those 3 lines of advertisement. The guy who's paying $5 actually has some reasonable thing to sell to you. So the offensive stuff, unless you're masochistic, you are not going to click on it. Okay? The fact that he's paying $10 is of no use if historically nobody is clicking on this advertisement. Right? So this brings up the issue that essentially you should not be ranking, that should not be showing the queries, the advertisement of the biggest bidder, but advertisements of the bidder times the probability that their advertisement will be clicked on by a user. The expected return, okay, right? Expected return. Okay, so now how do I get the expected return? I need to figure out some historic way of keeping track of who are clicking on these advertisements from this particular advertiser. Okay, suppose I kept track of those. So for example, and I kept track of these probabilities. I learned these probabilities. The first few times I'll take a hit and then I'll be showing probably the guy with, that's why this is very important to randomize. If you kept only showing the $10 guy, you would never make any money, neither will you learn anything. You would probably think that nobody ever sees any advertisements, you will change your business. Right? So what you really need to do is when you are learning, this is a very deep point, when you are learning, you need to explore. Okay? So in the beginning, you probably have to show some of the other guys once in a while, just so that you will get the click-through rates. So you learned that, and you have this information saying for this, for this kind of advertisements, people are clicking on it with a 0.1 probability. These guys' advertisement, they're clicking on it with 0.5 probability. The better these numbers are, and the better they are going to be, the more exploration you have done. Right? The better those numbers are, the better your expected numbers are, as to how much you are expected to get if you were to put this guy in as the advertisement for that page. Right? Okay? So now this click-through rate is measured historically, and now the simple solution is, instead of raw bids, use the expected revenue per click. Now the new online algorithm is still greedy, except greedy in terms of expected value rather than greedy in terms of just the maximum value of bid. Once again, you can't do any better probabilistically than this.
Should be expected revenue per showing.
No, not showing, for clicking. Because the point is, you don't get any money for showing the advertisement. That's the whole point of search engine advertising.
But expected revenue per click.
No, so what I'm saying is, when you are putting in the advertisement, you are trying to ask yourself, how much money can I expect to get from this advertisement? And that depends on the expected number of clicks times the bid. Okay, so if the probability of click is 0.5, then each time I show, I expect about 50 cents. And here I expect 0.2, 20 cents. Okay, fine. So again, it's an online algorithm, and it's probabilistically optimal. So showing you all the advertisements, all the queries up front couldn't have made your performance any better than than this online version. Notice that you could do bad online algorithms. Okay, so for example, I will pick, in the previous case, I don't like the big versus small, I'll just pick the medium bids. That would be an online algorithm, you'll get medium revenue. Unless you wanted to get medium revenue, in which case, of course, the optimal guy will pick the optimal, one, so your competitive ratio sucks. So you can make bad online algorithms. Till now, pretty much the obvious online algorithm turned out to be also the best. Okay. Next, so anyway, this is an example of this, and I don't know that you really need to go through this that much, but if there are 3 advertisers A, B, C for this query, one is paying $1, 75 cents, 50 cents, then if you don't have the click-through rates, you will essentially show probably A. Not probably, you will show A for that query. But if in fact the click-through rates for this guy historically are 1%, 2%, 2.5%, then you can compute the expected value of showing this ad. This is 1 cent, 1.5 cents, 1.25 cents, and so you'll show that first. This was a huge, big difference in search engine advertising, because in the beginning they were showing the first one. The overture was doing the first idea. And then a little later they started actually keeping track of click-through rates and started doing the second one. Remember that while if I were to give you the probabilities and you ignore it, I can make fun of you. If I didn't give you the probabilities and you did not get the idea of tracking the probabilities, it's, that's very much likely that you didn't think that you need to learn anything more than what was provided in the specification of the problem. In this case, you have to explore and learn the probabilities, click-through probabilities. That's an interesting learning problem. But the right way to learn this, that's a very interesting question in itself. But you can think of some reasonable ideas. Okay? So, that's complication 1. That's complication 2, right? I got 2 complications. No, that's complication 1. Good. I'm just worried that my complications are complications. How many of you have seen Brazil? Okay. The second complication I'm going to look at is that advertisers are actually bidding on keywords, not on queries. Okay? And in fact, that's what happens. In fact, the idea of bidding on queries can be a few words long. It can be a large number of words long. So especially when search engines are showing you advertisements for your emails, there is no query in the email. The subject is not a query. The body is not a query. And yet they somehow try to say, well, if you are looking at this kind of emails, you may be interested in looking at these kinds of advertisements. So in essence, they're sort of doing some kind of a keyword-based showing of advertisements. Okay? So that basically, if you are doing, advertisers are doing keywords, then in essence, multiple keywords might match a particular query. Okay? And so, in fact, there is that complication. So basically, it's tough. Each query and the different bits for that query, and each query has different keywords, and each keyword set has different bits. Okay? And then one way you could do this is that if you have keywords, essentially, first of all, you need to figure out. So here is what happens. So I have my query or page content. Okay, our mail content. And then the users, the advertisers have said, if you have K1, K2, show my advertisement, I'm going to pay you some money, okay, 50 cents. And if you have K3, K4, K5, I'll pay something. And when you have multiple keywords, you can also think of them as search phrases. Okay, so then the question, of course, is, they did not bid on this query. I need to figure out whether to show this or not based on whether these keywords are similar to this query. That's the IR problem. Right? So in essence, to support this, you need to, first of all, pick top case similar advertisements to the query, and then among them, and sort them in terms of the CTR times the bid for those, and then show the one with the highest. That's the basic idea. But to be able to do this, notice now your IR stuff that you've been talking about before comes in. First of all, you can do exact matching, keep Boolean-based matching. You can do vector similarity kind of stuff. You can also do query rewriting. For example, if somebody says digital camera, okay, then you may be able to rewrite. So if somebody says just say camera, then you may be able to say rewrite this as camera, digital camera. That means I added an extra word. That's like query elaboration. At that point, then it might exactly match something. Do you see what I'm saying? So the entire set of how do you decide whether a page is similar enough to a query, you can also play the same game and say whether a query is similar enough to an advertisement. And if it is similar enough, you want to show it. Okay? You want to show the ads that are similar, presumably because otherwise the users are not likely to click on them. Okay? And among them, you basically take the big times CTR to pick the one advertisement that's the best. Okay, it should just that one. Right? That's the complication 2. Okay. Now, complication 3 is that I might actually want to show more than one advertisement per query. Why should I show only one advertisement per query? Okay, so I can have advertisers bidding on keywords, and I want to show multiple advertisements. That's what you see right now. Okay, obviously, if you show 1,800 advertisements, it's completely useless. Okay, so you probably tend to decide upfront. When the search engine decides, maybe I'll show at most 5 advertisements. You also see that for some queries, they show more advertisements than other queries. Right? Okay, so you may want to show multiple advertisements. Now, the interesting thing is the moment you are showing multiple advertisements, it's the same issue. If I need to show you a single best document that's similar to the query, you pick the document that has the highest vector similarity. Let's say. If you are going to show 2 documents that are similar to the query, it's no longer the case that the second one is going to be the one with the second highest vector similarity, but rather the one which has the second highest residual similarity. That means it's not only similar to the query, but far enough from the other advertisement. Far enough from the other document. Okay, so that's one issue. Okay, the second issue in the advertisement, it's actually also an issue for the search results too, but even more so for advertisements, is that so basically if I look at an advertisement that's very similar to the second one is very similar to the first one, I'm probably not likely to click on it. Even if I saw it in isolation, I may have clicked on it. Okay, that's the issue of ad similarity. The other thing is that the first advertisement was so offensive that it turned you off browsing. You wanted to shut off the computer and go have a cup of coffee and then start thinking about world again. In which case you abandoned search. If you abandoned the search, the second guy is waiting for customers to come. It's like there's a long line of in a small thin road with a long line of shops. The first shop guy was so offensive that everybody is not even entering that street. So all the other guys who are nice and polite and are selling good stuff will never get any customers. Right? So there's this question of abandonment issue, whether people will just stop browsing afterwards. All of these will come into play when you are trying to decide how to rank the advertisements. Until now, you did not rank the advertisements. You are only showing one. You now are showing multiple advertisements per query. Okay? So you need to worry about the inter-ad correlation, which is a diversity issue. You also need to worry about the user browsing patterns. In the sense, the user might just get sick and tired of browsing and stop, after some. Okay. So those two have to be taken into account in ranking the advertisements. Okay. Now there is Raju who's sitting here mostly to check whether I'm making sense at all, because he actually knows this area much better than me. And he has done some work earlier on actually what's the right way to rank results when you're taking into account both the inter-ad correlation and the browsing abandonment probabilities. In particular, he actually points out that if you are taking inter-ad correlation, that is the diversity issue, into consideration, then the optimal ranking is NP-hard. And you don't want to do NP-hard computations at the time when you're showing the answers to users, at least not optimally. And so if you ignore that, then he essentially says for each advertisement, you can compute a score which is based on the bid amount and the abandonment probability and the relevance of the ad. And then you can rank the advertisements according to this score, and then that would be out. Okay? Now, if you're interested, ask him more, but I'm just trying to show you that it becomes more interesting than just picking one ad, and then you need to consider that interrelations. Okay, so that's that. Complication 4. Up until now, online is no worse than offline. Really, if you had sense, you could get your competitive ratio to be as high for the online algorithm. I mean, the competitive ratio to be 1, basically. Okay? The question then is, when does it become not possible? Here is one example. Advertisers have limited budgets. Okay, so in fact, when you go and make an advertisement using your, maybe everybody, I think Google puts $10 in your account anyway, and you can make an advertisement for $10. If you just say, go ahead and pay, and here is my credit card number, then, by day after tomorrow, all your friends who heard this kept clicking on your advertisement, you ran out of all your money, and you have no money, you drop out of grad school. And so make money. But that's a different story. So the point is that you have budget restrictions for individual advertisers. This winds up making the problem not equivalent to so the online version of the problem now no longer has the competitive ratio 1. Okay, so to understand this, take the following simple example. So again, assume that bids are 0 or 1. So everybody is bidding, 1 for every advertisement, every query they want, and if they don't like it, they'll put 0. Okay, and all the advertisers have the same budget B. Simple case. Okay, and but B is not infinity. That's the important thing. We assumed essentially infinity before. Okay, B is finite. Okay, so and I'm showing one advertiser per query still. Let's try so now if I'm doing greedy algorithm, either based on CTR or just based on bid. For now, assume CTRs are all 1. Okay, because that complication is sort of orthogonal to this, at least right now. Okay, so you have A and B, and A bids on query X, and B bids on query X and Y. Okay, and so of course A bids, A will give you $1 if you show his advertisement for X, and B will give you $1 if you show her advertisement for either X or Y. Okay, now both have budgets of $4. That's it. So after 4 advertisements, they can't pay you any money. Okay, suppose my query stream is this. From now until midnight, these are the queries that are going to come. X, 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 and Y, 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 Y. If you know all of them, you know what's the right thing to do. Do you not see it? Right? Because you should save the Y's. Okay? So basically, because B can take either X or Y, and A only likes X. So if you start using up all your B's here, then you have nothing to show after this. Do you see what I'm saying? Right? Had you seen all the queries, unless you've been dropped repeatedly on the head, you would have realized this. And you would have realized that you can make as much, basically you can show 4 plus 4 advertisements and get $8. That's what you could get, assuming CTR equal to 1. But if they're coming one by one, you don't know the future. Okay, when I just show you X, you have no idea what's happening behind the X. Okay, that's what the case before too. And yet you could do greedy before and get away. Here if you do greedy, you could very easily get into trouble because you could do pretty arbitrarily bad competitive ratios. In fact, how bad can it get? It turns out stupidity also has like a bottom line. It turns out that the worst case greedy choice is putting B in the beginning for this case, all B's. In which case you get $4. Out of a total of $8 you could have gotten. So your competitive ratio is half. Okay, half you can get. Okay, the question is, can you do better? Optimal obviously is A, B, B, B. But you can't really do optimal unless you knew the queries, unless you knew the future. What's happening here is hindsight optimization. You figured out how the future evolved and then said, I could have done slightly better. Right? Online algorithms always have to do this. By the way, many things that we'll talk about in today's class, they're much more general than just search advertising. That's sort of true for classification too. It's more general than IR. Okay? And similarly here, online algorithms come all sorts of places in computer science. And whenever you have an online algorithm, the question you're asking yourself is, what is its competitive ratio? That means, how well does it do with respect to an optimal algorithm when the entire input is known upfront? Okay? So in this case, if the competitive ratio is half, so the question is, can you do any better? Okay, remember the online algorithms can't think too much. They can't say if the second one is to be this, then do this. That makes no sense. You don't get to see the second one. You need to make a decision for the first one. So here is a situation where, in essence, I am giving you problems in midterm one sheet by one sheet. You really did not have the chance of looking at the entire midterm upfront. As soon as you say, I'm done with this problem, I'll give you the next problem. You still have to make reasonable decisions. So for example, here is a problem I gave you, and if it is already 1 hour, 12 minutes, and you're still working on this problem, and I told you I have a total of 10 problems to come, you probably are clearly doing something wrong. You're not optimizing. But neither are you optimizing it if you kept saying no, no, no to the first 9 and then spent all your time on the 10th one. Because you lost all the 9 problems marks. You see what I'm saying? And in life you do online decision making. And the interesting question is, can you still be intelligent? Can you still actually say the online decision making you are doing has worst case performance guarantees, that the competitive ratio is closer to 1? You know, that's the question. So that's a beautiful question. Okay, so it turns out for this particular case, it's a very simple idea that works quite well. Which is, you pick the guy, for this particular scenario, you pick the guy who has the maximum unspent budget left. So, first of all, you got a query queue, and there are 3 guys who bid on query queue. Okay, this guy only $1 left, this guy has $10 left. So you give it to the $10 guy, because you know, maybe this other guy, maybe that $1 he could spend it on some other query that you can make money off of. Notice that the search engines are not trying to make sure that people don't go bankrupt. They could care less. They would like all the advertisers to go bankrupt, and as long as they make money. The issue here is the $1 that you have, if you spend it on this, then you may not be able to spend it on something else, and I still have advertisements coming. And maybe you are the only guy who's going to pay $1 for cse494 advertisement. And so you're like a very precious kind of a guy. I want to keep you around. Okay? So I'm just going to look at how of the people, so of course you're also going to be, your $1 bid is also possible for some other advertisement about a movie. But I won't show you now. I'll show the other guy who has bigger budget left. This is not making any decisions about, it doesn't have any knowledge about the future. Did you see what I'm saying? It's not saying that some kinds of advertisements will come later. It's just saying, of the 2 guys, you can't do worse by giving it to the guy with more budget. Okay? And then break ties arbitrarily. If 2 people still, both of the guys A and B have the same amount of money left, then break ties arbitrarily. Okay? If you do that, in this particular case, if you do this in this particular case, and you can run this, balance would basically do this, optimal does that. Notice that the moment after it picks A, next time it can't pick A again, right? Because A would have less budget left than B, so it will have to pick B. That's all you know. Okay? So if you do this, then the competitive ratio for this case is 3/4. With this just simple change, the competitive ratio is 3/4. It's a huge improvement. Right? Okay, instead of half, it's 3/4. So you're making a lot more money. Who is making money here? Search engines. Who's designing algorithms? Search engines. And how much would they be interested in this? Of course, a lot. Okay? So the interesting thing is this idea anybody can, not anybody, I mean, you probably could have thought about this. Okay, there's a paper based on this idea and its generalization in JSCM, which is the topmost journal in computer science. The reason is basically they'll also show that actually in the general case, the worst competitive ratio for this idea, that is using the balance, remaining balance of the budget, the worst case competitive ratio would be around 1 minus 1 over E, or 0.63. It's less than 0.75, that's what happened here. It's not the worst case scenario for you. But it would not be 0.50 either, which is what the dumb algorithm does. Showing this is what got their paper, much more interesting than just saying it's 90. Okay? Yes?
If you also take into account the probability that any of those queries that these guys are bidding for is going to come in the future.
That's again, you can make, as I'm talking about each complication, you can have complications having complications. Or you can bring all the complications together. And that would change some of these things. I won't talk about it right now, but if you had that information available, you could do better, obviously. But this is completely agnostic to the future. It does not have any information about the future distribution of queries. If you happen to know the future distribution of queries and you decide not to use it, then, and if you decide to use it, then you can do better than this.
I'm not talking the future distribution of query, I'm talking about B builds on X and Y. So from the past experience of the query, you can tell what is the probability that, kind of insights the probability that...
Again, you're talking about distribution of how queries are coming. Whatever you do, you're talking about which queries are more likely to come in the future, which are likely to come in the past. So for example, even if I see, you know, X, is there a reason to believe that the next would be Y more likely than X? For example, I took a coin. Okay, here's something I want to ask all of you. I took a coin. I tossed it 15,000 times. It came heads. I'm about to toss it 15,001th time. We repeat it, right? I'm about to toss. What's the probability that it will come heads? 0.5. Most people in the world don't know it. This is why lotteries work. Okay, you go to Las Vegas, and people say that lotteries are the way of siphoning money from stupid people and give it to smarter people, right? So you go to Las Vegas and you'll say, oh, this thing hasn't come for a long time, so I'm pretty sure its time is up now. As if there is like some, you know, some budget on the heads and tails. No, there's no budget on heads and tails. Do you see what I'm saying? More important question here is, you are not making any decisions based on the distribution of the queries. I'm not saying you should, this algorithm doesn't. So any algorithm that uses less knowledge is going to be more useful. Anything which uses more knowledge is going to be less useful but might do better. Yes?
But I see a flaw in that. If you choose the one with most volume still around,
What?
that if you choose a guy that has more money in his volume, that probably means that his query has a very low click-through rate because it's a bad query.
No, again, no. You could do this whole thing instead of bits. You can also talk in terms of. So let me look at the next one. Okay, so here I'm assuming click-through rate is equal to 1, but the next I'll talk about the general case. Okay. Okay, so this is special case, and you can get 0.63 just by keeping track of the balance. More general case here is you have arbitrary number of bits. Not all bits have to be equal sized. Here in the previous case we assume each bit is $1 or 0. Okay, but you don't have to be. Some people might bid $4 for one thing. Okay, and not all advertisers have to have the same sized budget. Now, if you take that more general scenario, it turns out that if you directly apply the balance, which is the amount of money left, it doesn't look too good, because the guy who tends to bid, so if I have, this guy has $4 left, and this guy has $10 left. Okay, you would think the $10 guy somehow has more time to live. But suppose just 3 queries back, this guy had $10,000, and he's now $10. Which means he was doing huge bids. He's doing like, $7,000 for this query. So this guy's fraction of remaining budget is what you want to think about, not how much money is left. Previously, the fraction of the remaining budget is the same as remaining budget because you started with the same amount and your bids had the same size. Okay, so to generalize it, essentially, and I won't go into all the details here, to generalize it, if, for example, the bid is xi, you can, instead of thinking of bid value, you can also think of expected bid value, xi times CTR, right? Budget is bi, okay? And then the amount spent so far is mi, among the budget. Then the fraction of budget left over is fi, which is 1 minus mi by bi. That's the fraction left. Okay, so then you make this quantity, which is sort of balanced, expected balanced budget, which is xi times 1 minus e power minus fi. Okay, it has the correct qualitative properties. And essentially, if you use this and decide whoever has the maximum this value will get the next, will get picked. Okay, so notice that in this case, if this guy is paying $10 for this query and probably used up most of his money, I may still pick him because everybody else is only paying $1 for this query. Previously, everybody who is bidding for the query was paying the same amount. So there's no difference in terms of bid amounts. Now there is. Okay? So you consider the bid times or the expected bid times the amount of, normalized amount of fraction of budget. Okay? And if you use that, it turns out that if you give the query to the bidder with the highest such value, then it turns out that's a generalized online algorithm. And that too will have a competitive ratio of 1 minus 1 over E. And to understand the proof for this is obviously very interesting. I'm not even going to go into it. You can actually go and read that paper. Partly you can get an idea of exciting stuff that gets done, in various areas. Okay? So that's to handle this complication of budget constraints. You need to come up with a more interesting online algorithm. It's still online. It's not making any assumptions about the future, but it's being smart. Okay? That's possible. Complication 4. Yes?
Click-through rates can be used in adversarial ways, right? And I can keep some budget, like...
I understand. Yeah, that's fine. I mean, we'll not get it. Yes, in some sense. So your point is that I can change click-through rates for my competitor's advertisement by clicking it a lot.
No, not like that. I can keep some budget for, like, I'm a very popular brand, so I will keep per bid rates very low, and still my click-through rates will be high. So even if my competitor has a good bid value, it will not be shown.
That's fine, but that's search engine doesn't care. Search engine wants to know how much money they're going to make. So so the thing is, it's not adversarial. If in fact, Apple made iPad and HP made some other pad, right? And they both, in fact, one is cheaper than the other, nobody was buying this other thing. And would I say that somehow Apple was being adversarial? Not necessarily. I mean, they have done enough adversarial things in their lives, but this wasn't an adversarial thing. They just made a very good product, and nobody else wanted to buy the other thing. And so there's a higher click-through rate for that. Okay? But in general, by the way, this class of all the things, there should be a million questions like this that you should be thinking about. If not, I would be surprised. Okay? I mean, in general, because it's a pretty open-ended set of discussions that we're doing here. And again, you do this, you see this all the time, and you have reasonable intuitions, and I won't be surprised if you figure out all sorts of extra complications. But let me go through my complications. Oh wow, this is my last complication actually. So this is the balance. This one actually, the interesting thing is that you no longer could do online. So you needed to be smart about doing your online. Okay, that's it. Now, the last competition that I'm going to talk about is how do we encourage truthful bidding? This is actually a problem anytime there are auctions. Okay, just as the idea of generating good online algorithms is a problem anytime you are seeing the future piece by piece by piece, and you have to make decisions for this part before you get shown the next one. And it just happens that here our class intersected with that deeper area. Okay? The second question is, another kind of a complication like that is, look, we are making our entire decision making, that we being the search engines, are making decision making based on the bids that people are submitting. Now, how do you make sure that people will bid their true worth of that item to them? Did you understand what I'm saying? Okay, when you are taking part in bidding, there's always this worry. There's always this worry that maybe I shouldn't bid all the things. I mean, suppose this thing is worth $10,000 for me. Maybe I don't want to open my mouth and say $10,000. Because maybe nobody else cares about it, in which case all I need to do is hang around, and if nobody says anything, then I'll get it for $1. Right? So the whole issue in auctions is basically you have to design a mechanism. This is a very deep issue. You have to design a mechanism where people cannot do better than being truthful in that mechanism. Do you understand what I'm saying? So if you design a mechanism where by lying they can do better, they will lie, because that's part of being smart. Do you understand? Whatever your preachers say, you should be really happy that you know how to lie, because you understand that your brain is different from my brain, and everything in your brain is not in your brain. And so I know something, but I will tell you something else, and that's ability to be smart. Okay. So the question is, given that you are dealing with smart people, which is all humans, it turns out, then how do I make sure that they are actually willing to be truthful? Okay. This is the place where we intersect with game theory. Game theory is all over the place. Okay. So this particular part of game theory we're interested in essentially is how do you make sure that, so if they don't do truthful bidding, what happens? So for example, suppose I want to bid $2 per click on the phrase best ASU course, let's say. Okay? But if nobody else cares about this, why should I pay $2 to Google? I may want to just pay 1 cent if I'm the only guy. Right? So how do I know that I'm not overbidding? The big issue in auctions oftentimes is what they call buyer's remorse. Okay? You get what you wanted, then you start thinking, oh man, I bid too much. What am I going to do with this junk? Let me just turn around and put it back on eBay and sell it higher. Okay? And hope that there are stupider people than me. But the point is, the question is, you should, in the optimal auction, you would be able to, when it's a well-designed auction, you will get the item and you would be happy. Because you gave away the money, that's worth to you, that represents the worth of this item. Okay, so you won't overbid, you won't underbid. That's what you need to do. Okay, but I would be thinking $2 is the true worth of this advertisement, right? But I might be thinking, what if other people don't care about it? If I say $2 up front and nobody cares and Google still charges me $2, I'm probably going to take this into consideration next time around and underbid. If I underbid, I won't get my advertisements, my items. By underbidding, you're reducing the chance that you get what you really want. B, the auctioneer is not getting as much revenue. If everybody underbids, then you're selling stuff for less than their true value for the for the society. Okay, everybody individually making decisions in their own best interests. If you can somehow design a mechanism such that people will still do decisions such that the societal happiness will increase. That means both the auctioneer is happy and you are, the guy who gets the item is happy, right? That would be what you want to do. Okay, so the classic idea that you would have thought, if everybody is bidding, like, if I bid for $2, so assume that, I'm going to bid $2 for this advertisement, you bid $1, you bid 50 cents, the first idea would be